Fragmentation. We can use a tool to slice up our packets. This makes it a challenge for stateless filters, because as you look at that first fragment, you got IP header, TCP header, and data, but look at the fragment. The fragment has the IP header. Where's the TCP header? There is no TCP header. The TCP header identifies what service to send the packet to. So without that, a stateless filter is lost. So that's why fragmentation attacks are still popular, because they can get by filters, they can be harder to detect, and are used for evasion. Buffer overflow. Buffer overflows have been around since software's been around. Programming languages, all this other type of stuff, buffer overflows. Now we can blame the programming language or we can blame the programmer. It doesn't matter. They're a fact and a reality today. The main thing to understand from our hacking standpoint as a red team hacker, we need to know 3 components, and have 3 components for a buffer overflow. We need a return address, where the location of the instruction pointer is at the time of our execution of our shell code, and then a payload. So we need a return address, a shell code, and a payload to conduct buffer overflow attacks. Well, because a program uses a data structure called a stack, which is a last in, first out, this is how we actually corrupt memory. The code writer or programmer is responsible for policing their own stack. This has led to many vulnerabilities. Why? Some programmers can be lazy, not write good code, or not run it through a good compiler, or some people blame the language, but it's mainly the programmer. More concerned with making it work than writing secure code. Now, I come from a programming background. I can be honest with you, when I used to write code in the late 80s, all I did was want to make it work and go home. I didn't want to chase a semicolon at 3 o'clock in the morning for 2 or 3 days. I just wanted my program to work. I didn't think about somebody trying to break it, and that's reality. Well, what's the stack? The stack is a fixed size that's created by the programmer when we write our code. It stores the local variables of the program, stores the data inputted by the user or system. This is the problem. It's a finite size. So if it's going to store the data that the programmer allows it to store, the only safeguard is the programmer. The data copies up and the stack grows down. Here's a simple C program example for you. And we got there in red, bad programmer. Because see how he says gets? That stands for get string. Well, get string has an argument where you can tell it a format specifier, but in this case, we're just get string buff, which means we're not doing what we call boundary checking or type checking. We're not checking the type inputted by the user or the attacker. It could be an attacker. So we say input your name. A bad programmer says get string buff. Well, buff is just an arbitrary area of memory that has character space. Well, if we put in there, in this case it's 4 characters, well, what if I put in 10 characters? Well, all he does is put string buff, which would display it on the screen. So if I put in 4 characters, the program's fine. As we'll see in this this is an example of a stack frame. And this is our program stack frame. As you see here, we got main function, we got arguments, we got that buff. And buff is just a temporary storage area. It's a storage area for data inputted by the programmer, by the client or the user. And then the overflow function. So that's our actual stack frame for our little simple program that we're giving an example of. So what happens if we go input your name, right? So here we go, we're showing you the function overflow in what's called a debugger. So even though we're emulating the medium threat and below as a red team member, we need to understand debugging and debugging of code, because sometimes we'll have to figure out where the actual program overflow is to craft an input. Remember, we still might have to write our own exploit or a buffer overflow, because maybe we'll find a vulnerability and then no exploit exists. So this is actually just a simple debug, and I'm not going to go into all the actual semantics of what it is. There's plenty of references and books out there. The main thing to look at, though, is see how that function overflow, that shows you the overflow, and it's a call to function overflow, and that's the address in memory where the call comes. All right? So this is how we actually do our debug of code. So when you look there, you see the printf function, you see the get string, and you see the put string. And then you see the registries, that EBP, ESP, extended stack pointer, base pointer, all that. That's all registries that if you want to know more, get a good assembly language reference manual. So now here's what's going to happen. Here's our simple stack after input. All right, so we'll put it in here. We got our main, we got our arguments, we got 4 A's. We always love to use A's. The character A is what we use to test for buffer overflow. Don't ask me why, probably because it's the first character in the alphabet. Okay, if you wanted to use different, I've seen people use X. But anyway, doesn't matter. Okay, so as you see here is, in our buff, it's been stored 4 A's. A. This is our program. So as long as 4 A's go in, it's fine. But what happens if the user sits down and does this and enters not 4 A's, but 8 A's? Remember, buff only has 4 bytes of storage area. So when we look at our program now, there's our 4 A's. We're good. If the programmer would stop us right now, we'd be good. But if he doesn't stop us, what was located below that? The call to function overflow, which is usually used by a return address. Now, overflow's been written with 4 A's. So now when you think about it, well, what happened to the return address for overflow? It's gone. This is called a smash stack. Because this stack now, where this red arrow references, is called the instruction pointer. This instruction pointer points to an area in memory that should have the return address to our function, but what's it have? 4 A's. Since it has 4 A's, the stack has been smashed and corrupted because the return address has been overwritten. This is the holy grail for the attacking side. We want to know where this instruction pointer is when this code breaks into that return address, because we want to take control of that instruction pointer. The return address is gone. Now that we know the return address is gone, we start a trial and error period. And we create a bin SSH. So we do our A's, in this case we're trying 6 A's, /bin/sh. Why? We're trying to get the instruction pointer to execute bin sh, which is a shell. So now what we do is 4 A's, AA, /bin/sh, and guess what? The instruction pointer points to our code. We now have a buffer overflow. Now, that's a quite simplistic way of explaining it, but hopefully you understand it's just taking control of the instruction pointer because we overwrite the return address with what we call shell code. Now, the shell code can consist of a lot of other things, but it usually somewhere in the shell code will have an executable shell. In a Windows world, it's usually some shell that's going to run like command.exe. In the Unix and Linux world, it's bin sh. And that's the instruction pointer runs the shell. Now we have another attack called the format string attack. This is a result of a programmer shortcut. In buffer overflows, we have to find the return address. In a format string attack, the return address is easy to find. Why? Because we can walk up and down the stack because using format specifiers. It's often confused with a buffer overflow. It's often used as an attack after the format string finds the address, we do the buffer overflow. But a format string has a specific identifier that is a format string attack. And that is, I can enter format specifiers and return address information from the stack. So let's look at it. Here is a simple C statement. A good way to get input is represented first. Printf, enter your name. Get string, name, comma 16, comma standard in. Printf %s. That %s says format specifier string. That means string has to be in the value stored by fget string, fgets. Name has to have the value of a string. Boundary check type condition. As long as it's a string, that's good. That's a good programmer. A bad way is if I get the string there in the bad way to get input, and I printf, and notice in the printf, I no longer have the %s. This is a shortcut. It's a programmer shortcut, but often programmer shortcuts leads to problems. And this problem is now there's no format specifier. So if I don't have the %s there, that means I'm not doing a type check to make sure it's a string type. I can put in anything. In fact, I can put in hexadecimal. If I put in hexadecimal, it will display the return address. And that's what a format string attack does. Here's an example. Enter your input. I enter %x, %x. It's hexadecimal. So now what happens is X equals address. So the X is the address in memory. What's in red? The instruction pointer. So now I have the address to the instruction pointer, which is why I said in a format string attack, we can walk up and down the stack. Okay? And this is what it looks like, a format string in action in a debugger. So what I do is I do a /format, sorry, not a debugger, an actual compiled program. What is your name? I put in my name ABCD. It's fine, it prints name ABCD because I used a format specifier. Now I go, what is your name? I say ABCD %X %X. And it goes ABCD 10, the number of bytes on the stack, and B7F6B440, what do you think that is? That's the address of the instruction pointer in memory at the time ABCD is written. Therefore, I now have what? I have the return address, and now I can craft and draft and create a buffer overflow that will overflow at this B7F6B440 address. So what are some common services to attack? Ones that will give us privilege level access. If at all possible, we always attack a service that gives us privilege level access. Any service that runs as root or administrator. FTP, SMTP, most of them don't run as administrator, but a lot of times people make that mistake. But they're also always publicly available. We like that too. DNS, HTTP, Hypertext Transfer Protocol, I'll cover that later. It's just a short list. Any service can be attacked, but we always want to look for the ones at higher privileges. Why attack a service if we can attack another service that gives us root? Why attack a service that gives us user? Unless we only want access. If we can't get root, then we'll take user, but by all means, if we can get root, we'll always ignore user. If we can't get root, we got to escalate privileges to get admin or root once we get the service exploited. Buffer overflow, format string attack. FTP, modes active and passive, right? Anonymous could be there. So if you run into FTP when you're doing your methodology, check it. See if anonymous is enabled. A lot of times it is enabled. And then check for anonymous write. It's okay for organizations to have anonymous enabled, but they should never have anonymous write access. If they do, then we've got some things we can do in different attacks. Okay? Clear text. FTP is clear text. So what can we do? We can sniff the traffic with a protocol analyzer. Look for the username and password. You know what's better? FTP active mode always has the port 20 as the data port. So since port 20 is the data port, I can spoof port 20, send traffic. Some stateless filters will allow the traffic through because it's got a spoof source port 20, and they know they got an FTP server. They're allowing the 20 to come back because it's data. Again, it's red team hacking. We go through all the possible structured attack methodology looking for different types of things. You don't think you'll run into FTP configured this way, but trust me, having done 20 plus years of testing, it's always a chance it's there. And the one time you don't test for it, you'll miss it. And somebody else will find it, or the administrator in the debrief will laugh and say, ha ha ha, we had FTP open and you didn't figure it out. So always follow that structured programming or structured methodology approach. SendMail and SMTP, Simple Mail Transfer Protocol. SendMail, as I said earlier, is a lot of vulnerabilities in SendMail. Spoof email. If relay blocks are in place, then it blocks it today. For years and years and years, we used to love spoofed email because we could spoof email and send email as anybody. Well, some people did that. A stock lost a lot of money. People lost a lot of money, a lot of lawsuits, those types of things. So most people today block relay with SMTP. But you still can send email with SMTP using certain techniques. It's clear text. So we can sniff the information from the mail, the headers and the content of the mail. It's important to note you always want to test it. So how do you do it? Well, most cases, email servers run on port 25, Simple Mail Transfer Protocol. You will discover this when you're doing your red team hacking methodology and approach. You'll find what the mail server is running at. And you just telnet to port 25. You say hello with one L. Hello, H-E-L-O. Mail from, whoever you're sending it from, receipt to, whoever you're sending it to, and the data. You enter the data. In case here we're doing an inspection, be there at 8 o'clock Eastern Time. Please provide the following data. Admin accounts with admin passwords. The dot by itself means save the message, and then quit will send the message. And if it's successful, you know they don't stop relaying of email. Again, normally you won't see this today, but you have to test it from a red team standpoint, because maybe you can't do it for a non-existent address, but what if you spoof the email and send it to a legitimate person? A lot of times that will work too, because this is the process how mail servers, because remember, the internet was built a long time ago on the principle of trust. We always leverage that principle of trust to do our attacks. And this was determined a long time ago how to pretend to send email to someone else. So we try it out. DNS, domain name server. Now the DNS has been attacked and attacked and attacked. Why? Again, the internet protocol we're running today, TCP. When was TCP developed? Ratified 1972, last update 1981. What was the size of the internet in 1972? Not very big. Small. What's the size of the internet today? Huge, giant. You all out there probably looking at this have devices, mobile devices, iPhones, Samsung, all these other devices, Androids, all this cool stuff. Guess what? We're running the same protocol we ran when the internet was small, and now the internet's huge. So because of this, a lot of these protocols are based on the principle of trust. Our job as hackers and red team hackers is trying to violate this principle of trust and use it to our advantage and leverage it. So against DNS, we can do spoofing, which is we can pretend DNS, we can poison it, or do a denial of service, or a very famous attack for a long time was called Kaminsky or the out-of-bailiwick attack. And what that is a poisoning the DNS, as we'll talk about. Spoofing. We know there's no authentication in DNS by default, so I can pretend to be any site. Even encrypted ones. The user's the only defense. You've all seen this before. You go to a website and it comes up and says, I can't validate this site. And you click on, I understand the risks, confirm exception, add exception, all that type of stuff. You just accepted a spoofed or a man-in-the-middle attack. That was your one protection telling you that, hey, this certificate's not signed by a valid authority, and you allowed it anyway. So what we do here is we respond to the DNS query first. So in the example there, you see there's a query for EliteSecurityAndForensics.com, and there was a response. Well, as long as I beat the response for the actual query, I win, because DNS doesn't have any authentication by default. Now Server 2008 and beyond in the Windows world does have some authentication components, as does DNSSEC. Poisoning. Provide false information in the response, the server caches it. Well, the key here is you look at this diagram, when it caches it, it also has this thing down here called additional RRs. That stands for additional resource records. And what that is even though I queried for EliteSecurityAndForensics.com, some DNS servers will take what's in the additional resource records and cache it and store it. And guess what? In that case, we can put anything we want in that resource record. So I can put a DNS entry to PayPal and point it to my machine. So these are the problems with some of the DNS we can face. Okay? We also have the local machine cache. What that is, once we compromise the machine, we can poison the DNS and put in a local entry, because the DNS always looks at the local machine first. So if I put the local entry and poison the host, the LM host file in the Windows world, Etsy host file in the resolve.conf file in the Unix Linux world, if I post and I put information in there, say PayPal is at my address, guess what? All the PayPal queries goes to me. Again, these are ways to get around protections and hack. Poisoning. Additional records field, as I said, should be ignored. It's not always the case. Results in poisoning until the time to live expires. Some people's time to live can be long, 24 hours, stuff like that. So again, that additional records field can be used to attack. Here's the Kaminsky attack. He discovered that if recursion's on, we can query the DNS server until the transaction ID is determined. It's typically 16 bits, is 65,536 combinations. So we also need the ephemeral port or the transient port that is being used for the query. Okay? So as you look at the example there, we have the source port, 54809, destination port, and we also have the transaction ID. So the 16-bit field, the transaction ID, and the ephemeral port, because ports are 16 bits if you may recall, 65,536, 0 to 65,535. So because of that, it's 16 bits. I can go through every possible combination in a pretty short time in a modern day computer. So once I predict these two things, the ephemeral port and the transaction ID, I can send out a response to that actual query and poison the DNS. And we do it by generating subdomain queries until I can predict the values. When you think about it, this is because recursion's on. Recursion being on means I may not know, in this example here, kevincardwell.com, I don't know all the domains, the subdomains under that, so I just start doing A, B, C, D, and keep doing it over and over and over again until I get enough to predict the transaction ID and the ephemeral port. Now, it's not 100% success rate. I've seen the Kaminsky attack take 3 days. But when it works, it's extremely powerful. And it's something that as a red team hacker, if you find recursion on, you should go and start trying some of these resource attacks like the Kaminsky attack. Now we're going to do a lab attacking services.